arc length. In this section, we're going to use the definite integrals to help us find arc lengths of plane curves. And for right now, we're only going to consider curves that are graphs of functions. All right? So what we want to do is we're only going to consider special curves. We're going to only consider smooth curves. And a smooth curve is this. If a function f has a continuous derivative on an interval a, b, then f is smooth. So what that's telling us is that the graph of y equals f of x doesn't have anything nasty in it. There's no breaks, there's no corners, there's no cusps. It's a really nice function. Alright, so let's figure out arc length. Let's let f be a smooth function on an interval ab, and let p be a partition of that interval ab. Also, let L be how long the curve is from x equals a to x equals b. So now if we look at a kth subinterval of AB, here's what we have. Here's our kth subinterval. We can talk about this distance here we've always called delta x sub k. Well, let's let this distance from here to here be called delta y sub k. Then we can say that the length between this point here and this point here is equal to delta x sub k squared plus delta y sub k squared. Alright, now let's do a little algebra. Let's take this equation and factor out delta x squared. And that becomes this. Now I can pull delta x sub k outside of the radical. And this right here is the slope of this line right here. And that slope we can approximate with the derivative of our function at c sub k. It's a great approximation. They're really close to each other. So I can say that the length of this little segment right here is approximately equal to delta x sub k times the square root of 1 plus the derivative at c sub k squared. Alright, so to get the approximate the length of that whole curve from a to b, I just sum up all my intervals from k equals 1 to n. And if you look at this, we can just rewrite that by bringing the delta x sub k on the other side. And this is just a Riemann sum for the function 1 plus f prime of x squared over the interval ab. So that leads us to say that if f is a smooth function, then the arc length of the function from a to b is integral from a to b of the square root of 1 plus my derivative squared dx. Now, we could do the same thing by integrating with respect to y. We just need to change our function to g of y and our limits of integration and make sure we integrate with respect to y. So let's do an example. Let's find the arc length of this curve from the point 1, 1 to the point 2, 2 times the square root of 2. Now, we can solve this problem in two different ways. Here's the first way. We're going from the point 1, 1 to 2, 2 times the square root of 2. And our function was y equals x to the 3 halves. In order to use our formula, we need to know the derivative, so I go ahead and take my derivative. Here's the formula for my arc length. I'm going from a to b, and I'm doing it with respect to x, so a is going to be 1, and b is going to be 2. And then I'm taking the square root of 1 plus, I put my derivative here, and then I square it. Now take a moment. You can simplify the underneath the radical. And now using u substitution, we can go ahead and solve this. We will let u be equal to what's underneath our radical. Once we've done that, we evaluate du by taking the derivative, and we get that it's 9/4 dx. Don't forget that dx. And solving this for dx, we get that 4/9 du is dx. Now when I do the substitution method on a definite integral, I also need to change my limits of integration. So when x is equal to 2, my upper limit, I get that u is equal to 11/2. When x is equal to my lower limit, 1, I get that u is equal to 13/4. So now I take all this and I make my substitution. My original integral now becomes the integral from 13/4 to 11/2 of the square root of u times 4/9 u. This is something easy for you to evaluate at this point, so go ahead and make sure you can evaluate this and get our final answer of 22 square root of 22 minus 13 square root of 13 over 27. Alright, so I said we were going to do this another way. The other way is we're going to do our integration with respect to y. So I have y is equal to this, is what they gave us. If I want to integrate with respect to y, I need to rewrite my equation so that x equals a function of y. So that becomes x is equal to y to the 2/3. Now I need to find the derivative of this. So I take the derivative and I get dx dy is equal to this. Here's my formula for arc length. My c and my d this time. C is my lower y value, so 1, and d is my upper y value, which is 2 square root of 2. So there they are here. And now I get the square root of 1 plus my derivative squared dy. We simplify what's under the radical sign. And now we'll do a u oh, actually, before we do that, oh, that's a good point. Let's remember this, because this is a neat trick to remember. If I were to let u be equal what's underneath the radical here, when I take the derivative, I'd get some funky derivative with like y to the, what is it, minus 5/3, and that's not in there at all. So a straight u substitution isn't so great. Let's look at what we can do instead. If we factor out that y to the negative 2/3 from under the radical, then this is what it becomes. And now I can pull this y to the negative 2/3 outside my radical sign. It becomes y to the negative 1/3. And now if I do a u substitution with u equal to what's under the radical, look at what happens. When I find du, it's equal to 2/3 y to the minus 1/3 dy. There's that y to the minus 1/3. So this works out really nice. So I have y to the negative 1/3 here and a dy. So I'll solve this for that. There's the y to the negative 1/3 dy. So I get 3/2 du is equal to that. Now again, we're doing substitution on a definite integral, so we need to change our limits of integration. When y is equal to 2 square root of 2, we plug it in and we get that u is equal to 22/9. Now when y is equal to 1, we plug that in and we get that u is equal to 13/9. Alright, so now we're going to take that, our integral here, put in our u substitution, and now this is something we can evaluate. Take a moment and evaluate it, and when you're done, you should see that we got the same answer as we did when we used method 1. So it doesn't matter which method you use, whether you integrate with respect to x or with respect to y, you just want to choose the one that'll be easiest for you.